It's my great pleasure to have the opportunity to tell you about work that I've been doing with a number of collaborators, focusing on the circumgalactic medium of roughly redshift 2 galaxies. So I will jump right in. I'll try and acknowledge work by some of my junior collaborators as I go through the talk. All right, so I always like to start talks in a place where we can all agree. I'm hoping this is a statement we can all agree on. So baryonic processes control many of the observable properties of galaxies. So I think we might argue that dark matter really forms the scaffolding onto which galaxies get built. But if we want to understand galaxies as a whole, and certainly observations of galaxies, we need to understand a variety of baryonic processes. So in particular, we'd be interested to know how gas falls in from the intergalactic medium and accretes onto a central source to build up the ISM. We need to understand how galaxies actually process gas and form stars, and what those stars do to their surrounding gas. We know that galaxies drive galactic winds, and so understanding how these winds are driven, and also what their fate is, how they mix back with the circumgalactic and intergalactic medium surrounding them, are all really critical things to understand if we want to understand galaxy formation and evolution. Now, typically when people talk about these, they talk about the baryon cycle, because this is a cyclical process. So we have gas falling in, forming stars. Those stars exert a variety of different things, energy and momentum into the ISM, which we have supernova explosions, et cetera, and that can drive these galactic outflows, and that gas mixes back in, perhaps enriching the circumgalactic medium and intergalactic medium, which that gas can then reaccrete. So we can understand that this will change, for instance, the chemical evolution of galaxies. So there's a number of observations and theoretical arguments that are often invoked as to why this is important. So I'll just give you two really fast, because I think many of you maybe already appreciate why this is important. This is one that's very commonly discussed, the discrepancy between the dark matter halo mass function and the luminosity or mass function of galaxies, which is extremely well constrained at this point. We see not only that they potentially have a different normalization, but that they have an extremely different shape. And that is hard to understand if all you have is gravity, right? And so we believe that processes such as feedback, or perhaps how gas is accreted onto galaxies, may in fact sort of have a dominant effect in how much mass a galaxy can manage to form over its lifetime. Another set of observations that many try to sort of make sense of are the strong relation we see between the chemical enrichment of a galaxy, its metallicity, and the stellar mass that's been built. So here's a recent set of observations, or more recent set of observations, of the mass-metallicity relation at low redshift. And we can certainly understand that the rate with which galaxies drive out metals that have been formed inside the galaxy, but also the rate with which gas of potentially lower metallicity is accreted onto these galaxies is going to affect the gas phase metallicity of a galaxy. And so if we want to understand relations such as the mass metallicity relation, we really have to understand these baryonic flows. All right, so if we want to understand feedback, if we want to understand feeding, where in the universe should we look? I would argue that the best time to look is back in time to sort of the peak in the cosmic star formation rate density of the universe around a redshift of 2, when the universe was more active, and at least theoretically speaking, we expect would be also the cosmic peak of gas flows. And there's been a tremendous amount of discussion over the last decade, or maybe even 2 decades, about these two central processes, these two central types of gas flows that are critical to galaxy formation. So there's been a lot of discussion about feedback, how we drive galactic winds, what are the important sources of energy or momentum, where are they coming from? Is it coming from radiation pressure on stars? Do we need supernova explosions? What's really driving out mass from galaxies? But there's also been a large discussion about what the properties are of gas that actually accretes into the ISM of galaxies. And there's been a discussion, especially over the last decade, of the possibility that there's actually very efficient means of feeding galaxies through cold filamentary accretion streams that come in with temperatures that are largely unaffected by the virial shocks around these galaxies, or maybe there aren't virial shocks around these galaxies. And so you can actually relatively efficiently, perhaps, feed galaxies in the distant universe. But much of this is, certainly what I'm showing here are sets of simulations. Much of this is a theoretical construct. And so the question is, if we want to vet this, if we want to test these kinds of ideas, how would we go about doing it? And what I like to point out from simulations such as these, with these beautiful images, is that we would do well not just to observe the galaxies themselves, but to find a way to observe the gas that surrounds these galaxies, to look off the plane of the galaxies and see what's there, because that's going to give us a lot of information about the properties of these flows. All right, so what do we know so far about these two processes? There's actually not tremendous observational evidence for cold flows, so I'm not going to discuss that. What I'm going to discuss is evidence that we have for galactic winds and feedback, because that is it's a very large field. Okay, observations of galactic winds. So we know outflows occur. They're very, very common. People usually use the word ubiquitous when describing outflows. So we see them, for instance, even in the local universe. Galaxies with very high star formation rate surface densities blow off these amazing winds. This is M82. You can't give a talk on the CGM without showing a picture of M82. But more to the point, we can see observations of galactic winds in essentially the spectra of all star-forming galaxies in the distant universe. Okay, so I'm going to walk you through this plot a little bit. This is just a stacked spectrum of many, many galaxies from the distant universe. You can ignore for now the purple line, which shows the Lyman alpha emission profile, and instead focus on all these other colored curves. 0 kilometers per second here shows the systemic redshift of the galaxy, which is measured via different means. And what you note is that all of these different interstellar absorption lines are all blue shifted with respect to the systemic redshift of the galaxy, okay? This is extremely clear observational evidence of an outflow. So let me explain it. You have the continuum source, which is the stars of the galaxy. You're seeing the gas in absorption, which means the gas has to sit in front of the continuum source. It's blue shifted, so this gas is moving away from the stars towards us, so it's flowing out of the galaxy. Okay, so it's like a very, very simple, very clean observational signature of outflows. If we had the opposite, if we saw a very strong redshifted absorption, that would be a signature of cosmological accretion, okay? We always see this blue shifted absorption in high redshift galaxies. Basically, all high redshift star-forming galaxies have galactic winds. Okay, we also have some evidence that these winds may travel to relatively large distances from galaxies. So this is work that we published in 2010 using background galaxies as flashlights against which to observe the absorbing gas in the surrounding foreground galaxies. And what we see is that there's a lot of gas down the barrel to galaxies. But then as we look off the plane of the galaxy, we actually still see considerable absorption in both neutral hydrogen and a variety of metal species. But at a distance of around 50 physical kiloparsecs, or roughly the virial radius of these systems, we stop being able to detect this very clearly. That's not necessarily a signature that there's not gas there. It has to do more with how we're doing the observations. And in reality, if we're interested in asking the question what the gas looks like on these larger scales, what we need is a better background probe. And so we need to go to a brighter background source. And so that's basically the entire point of the talk I will give today, which is using background quasars as this light source in order to get a really high fidelity probe of the gas and absorption. All right, so a little schematic of how that works. What we can do is point a very large telescope with an extremely high dispersion spectrograph out at one of the brightest quasars in the distant universe. So we literally pick the 15 quasars that are brightest in the sky around a redshift of 3 that are accessible to Keck. These are the best targets if you want to get high signal noise spectra. We do very dense galaxy redshift surveys in the same fields, focusing on galaxies selected based off of their UV colors so that they're bright enough to be able to be observed and we can get good redshifts for them. And then for any galaxy that lies in the foreground of the quasar, close to the quasar line of sight, if this galaxy has gas surrounding it, it will leave a very specific spectral signature at its redshift in the spectrum of the quasar. So for every single quasar, when we have a whole bunch of galaxies at a whole bunch of different redshifts, we're able to measure the gas and absorption around each of these galaxies. Is this clear? Nothing will make sense if this is not clear. Okay, perfect. Okay, so this is the schematic, but just a little bit more details about our observations because they took a long time and that's the whole reason why these studies are possible. So So this is called the Keck Baryonic Structure Survey. As I mentioned, it's 15 fields across the sky with basically the brightest high redshift quasars. And it's designed specifically so that galaxies that lie in the foreground of these quasars probe the sort of peak epoch of star formation. For all of the quasars in our sample that I'll tell you about today, we have really, really beautiful quasar spectra from high-res on Keck with 7 km/s resolution, and signal noise typically in excess of 100 for the Lyman alpha region and redward of Lyman alpha. And then we pair these with extremely large galaxy redshift surveys. We have spectra for well over 2,000 galaxies at this point in these fields, although you'll see how the numbers get smaller. So roughly 900 of them lie in the right redshift range that we can get really detailed CGM constraints. And so some of the work I'll tell you about is focused on this sample, but the vast majority of the work I'll tell you about today is actually focused on the 8 galaxies where we actually managed to probe them within the virial radius, okay? So these are a very special little select set where we can talk unambiguously about gas that actually lies within the halo of these galaxies. All right. Okay, so I told you these are galaxies. They're selected based off their UV colors. This is a whole bunch of like random observer speak. What are the actual properties of these galaxies? So they're relatively luminous galaxies. It's hard to find low luminosity galaxies in the distant universe and characterize them. So they all have luminosities of roughly L star at these redshifts. It's a high redshift study, so the ages of these galaxies are young, but they have a pretty wide range, anywhere from sort of a dynamical timescale in these galaxies up to roughly the age of the universe. They also have a wide range of star formation rates from a few solar masses to several hundred solar masses per year, and a relatively wide range, again, in stellar mass. Clustering analysis done by Ryan Trainer has showed us that these galaxies typically sit in dark matter halos about 10 to the 12 solar masses, which corresponds to a virial radius of about 90 or 100 kiloparsecs. So this is a good number to keep in mind for scale during the talk. All right, so jumping into results. Okay, so the high redshift CGM, what is the CGM and out to what distance does it extend? Okay, so in 2012, I did a deep dive into the neutral hydrogen distribution around galaxies at redshift 2. And this is one of the key plots from that paper. This is showing the characteristic column density of neutral hydrogen, so how much neutral hydrogen there is, as a function of impact parameters. So this is the distance, the projected distance between the galaxy and the quasar line of sight along the plane of the sky. And what we see, these are sort of the binned observations of the galaxies shown in asterisks. And what we see is a very strong uptick in the amount of neutral hydrogen close to galaxies. We see, in fact, about 1,000 times more neutral hydrogen within 100 kiloparsecs of galaxies within the virial radius than at random locations in the intergalactic medium, which is shown by this solid blue line. We see this sort of strong uptick within a few hundred kiloparsecs, so past the virial radius scale, but not much past it. But interestingly, we saw this excess neutral hydrogen signature on scales out to in excess of 2 physical megaparsecs. So on the face of it, that might seem odd. I don't think certainly neutral hydrogen gas has come out of these galaxies out to 2 megaparsecs. That's not physically possible. But instead what we expect is that this is a clustering signal. So these galaxies are relatively massive in the distant universe. They sit in special places, and there's large scale structure around them, and that's what actually we're detecting here. But an interesting question is how much of that large scale structure are things like filaments, and how much of it is stuff that might be enriched, the circumgalactic medium of other galaxies. And so recently I had a graduate student from the University of Chile, Amber Roberts, who was working on measuring carbon-4 column densities as a function of distance from galaxies. So this is preliminary work by her showing the same thing, this characteristic column density. You can just pay attention to the large symbols. And what she finds, again, is a very large amount of carbon-4 close to galaxies that falls off as a function of distance. One other way to look at this is by looking at the geometric covering fraction of gas around galaxies. So this is for neutral hydrogen from my 2010 paper. Again, you see this sort of strong uptick, the CGM of an individual galaxy, and this large scale signal. And in carbon-4, we actually see the same thing. So if we look at the carbon-4 distribution, we see a strong uptick on small scales, and we see excess carbon-4 absorption out to distances of 1.5 megaparsecs compared to IgM, which is shown in purple here. So I think what this points to is the fact that we are detecting probably the circumgalactic medium of other galaxies, places in the universe that have seen some level of chemical enrichment that's larger than random. Yes?
So the purple is IgM.
Yes.
Why does it change per bin?
It changes per bin because of sort of the statistics of the sample. So it's not actually changing per bin. If you put an error bar on this, they would all be consistent with themselves. But that gives you some idea of the overall sample size that's used to make the measurement. So the sample size that we're doing the comparison here is Boxenberg and Sargent, and their sample size is like, I think it's 6 quasars. All of the carbon-4 absorbers is in 6 quasars. And so that's the sample size that's being compared to.
Does this depend very much on the velocity ranges that you choose?
It's a little sensitive to that, but it's like the overall value that you see is sensitive to that number. But this is a conservatively small number, I would say. If you go up to 700 kilometers per second, you see a higher covering fraction across the board. There you could be, I mean, it's just a larger window, but you do see the IgM increase, but not proportionally as much. And so I think that the conclusion is not dependent on the velocity window. The actual values are dependent on the velocity window.
Why do you say that's a conservatively small value?
So I don't have them in this presentation, but if you look at the velocity distribution of these absorbers, like you can fit sort of the velocity dispersion of the carbon-4 absorbers, and this is like 1 sigma value. It's not taking like many sigma or something like that. Okay. All right. So these are sort of some bulk statistics, which are sort of interesting. But what else can we say about the CGM? So what does the CGM actually look like? Okay, so you're gonna have to put on your spectroscopist eyes for this, because I don't have really beautiful images. But what we can do is take a look now at gas and absorption at a distance of 75 kiloparsecs from a galaxy, okay? These are complicated, so I'll try and walk you through them. What I'm showing over here are the actual quasar spectrum shown in black. Areas that are grayed out are contaminated, so you should just ignore them. The colored curves show the void profile decomposition of the absorption that's detected along these lines of sight, okay? So each one of these individual little curves represents some parcel of gas that is in some way coherent. And we can measure its properties by doing this sort of spectral fitting. So there's 2 main points that I want you to take away from looking at this. I don't expect you to remember what these things look like exactly, but there's 2 principal points. So the first, there's a lot of subcomponents that you see in everything except for this oxygen-6 section, okay? So across the ionization states of these metal species, regardless of which one you look at, you see very, very complex absorption, okay? So gas in the CGM is kinematically complex when you look at it at high resolution. So it's the first point I want you to take away. The second point is the fact that I had to say except for an O6, okay? So the oxygen-6 section of the spectrum, this is the highest ionization potential species that I can probe with these data. This looks considerably different than all of the other species here. It's a lot smoother, each component is broader, and there's a lot fewer components. And so what this is saying is actually the gas in the circumgalactic medium is multi-phase, okay? So we have at least one density and temperature set in this sort of lower ionization gas, and in O6 we're seeing something that's considerably different. All right, is there anything else we can say about what the CGM looks like? So the dream would be to have a setup like this, which is where we have more than one sight line passing through a cloud. I mean, the real dream would be to image the cloud. We can discuss that, but that's hard. But you know, the straw man dream is to have 2 lines of sight. That's at least something I can do that pass through that cloud. And in one case in the sample, we can actually do exactly that, and that's because of gravitational lensing. So this was the discovery paper of the fact that this very, very bright quasar already known in 1987 to be gravitationally lensed, okay? So we're gonna take a look at the spectrum of the CGM through these two different quasar lines of sight. Okay, so the schematic looks like this. I didn't do a lot of effort to make my lovely double sight line actually be gravitationally lensed, so apologies on that. They're clearly not straight profiles. This is lensed by a galaxy at 0.5. But the schematic looks something like this. We have our galaxy 75 kiloparsecs away. We see two images that would be separated by 400 parsecs at that redshift. And so what we can actually do is probe the size scale of absorbing clouds in the circumgalactic medium on this extremely small scale, but at a distance of 75 kpc, okay? So that's what we'll do. Okay, so these should look familiar. We spent a little while staring at these. So this is just a fit to the absorption systems along that A sightline, the sightline that's brighter. What I'm gonna do now is take the product of all of these Voigt profiles, and that'll stay as the colored curve, so that's a representation of the fit to the A spectrum. But I'm gonna replace the quasar spectrum with the B quasar spectrum, the lower luminosity one. Okay, that's what this is. All right, so there's a few points to take away. The first one is that the overall scale of the absorption in velocity space is roughly constant. So there's some sort of coherent structure in the circumgalactic medium that has a size scale larger than 400 parsecs that explains essentially all of this absorption. The 06 section of the spectrum looks identical across the two sightlines to the degree that we can probe it. So it seems that 06 absorbers have size scales, again, larger than this sort of 400 parsec scale. But if we look in detail at this lower absorption gas, or lower ionization gas, we see that actually they don't agree very well at all. So the detailed structure changes completely over 400 parsec scales. So the individual absorbers that I'm talking about throughout this talk that I'll report physical properties of, like temperatures and turbulence values, those have size scales that are extremely small, less than 400 parsecs. Okay, so what does that actually mean for our ability to understand this stuff? So I think what that means is that it's going to be challenging, but there is hope. So there has been a number of simulators who have started to think about small scale structures in the circumgalactic medium. So I'm showing work here by Evan Schneider and your own Drummond Fielding that have shown us that at least when you drive idealized winds in idealized simulations, you often produce relatively small scale structures, perhaps significantly smaller than this 400 parsec number that I've been giving. Now, of course, these aren't, this is not like a perfect representation of my observations because we're going out to tens of kpc here and the observations I'm reporting are at like 50 kiloparsecs. But nonetheless, the idea that there is small scale structure that occurs around cooling outflows is one that I think deserves more attention. There has also been some work focused on how you can reproduce this small scale structure in cosmological simulations. So this is work by Cameron Hummels, who has popularized and really started, in my view, a new way of running simulation, which with enhanced halo resolution. So the idea there is that you actually force higher resolution in your simulations, not just within the ISM of the galaxy, but also within the circumgalactic medium. And you can see that so this is just the exact same cosmological zoom box, but now run at very, very different resolutions. And you can see that the structure in the circumgalactic medium looks completely different. And Cameron would argue that these simulations are not yet converged. And I can't agree more, just looking at I mean, I'm not a simulator, but I feel like that doesn't look like convergence. But also, his highest resolution simulation is 500 parsecs. And so from my observations alone, I would argue that you need a smaller scale than that in order to resolve these structures in the CGM. So I think there's a lot of hope going forward. But I think what this means is that really low resolution simulations are not going to be able to be directly compared to these kinds of observations. Okay. All right, coming back into empirical results. How much gas is actually in the high redshift circumgalactic medium? Okay, so One of the bulk statistics that is often reported for the CGM is the covering fraction of gas variety of ionization states. So that's what I'm showing here. There's not too much that I want you to take away from this plot, aside from noting that when you go to relatively low column densities, you see very, very high covering fractions. There is a bunch of gas, and it covers a large fraction of the halo. But what we can do is actually use some really, really simple geometric models to sum up all of this covering fraction and try and make an argument about how much mass is actually contained within, metal mass is contained within the CGM. And so when we do this really back of the envelope kind of calculation, what we end up with is a number greater than 10 to the 7 solar masses. That probably doesn't mean much to anyone, so I'm going to try and put it into context. So if you take sort of the typical metallicity of galaxies and you multiply it by the typical molecular gas content in the ISM, you end up with this number being about a quarter of the ISM mass, okay? So the metal mass within the ISM, excuse me. So we're finding metals that are comparable to a little bit smaller than the total metal mass within the ISM. One interesting point, though, would be to compare this to the total metal yield of the stellar population. And I was really excited about doing this calculation, and then I became progressively less excited about it as I did it. Because I read more and more and more about the IMF-weighted metal yields of stellar populations and became less and less convinced that we know how to make this calculation. So there's just a tremendous amount of uncertainty in, for instance, the nucleosynthetic yields of 50 solar mass stars. Do those actually contribute metals to the ISM? These are things that I don't know a ton about, but if you read the literature about it, and I talked to some of my local experts, and it would suggest that we have maybe an order of magnitude uncertainty in this number. So don't take this with as though I know this confidently, but if you take sort of an expected value, then we would be missing maybe 75% of the metals that had been formed by the stellar population. Now again, order of magnitude uncertainty. So we might have found all of them, but we also might have found basically none of them. But I think as an observer, this makes me happy because that means I have lots of other places to search. So this is not surprising. There's ionization states that we can't probe with UV absorption lines, so there could be gas that's hidden, that's much hotter. But more to the point, there's gas probably at larger distances that are not, this is just summing up what's in the halo. And I'll show some examples where I think gas is actually escaping the halo of these galaxies. So, so it's not surprising to me that these, some of the metals might be unaccounted for. All right. The next question I wanted to address is the physical conditions within gas in the CGM and how that can tell us something about accretion and outflows. Are there any questions at this point, or are you guys okay? Yeah.
So how many, you might be getting this, but one, I'm wondering how many clouds you're predicting along the line of sight with that size, and also what you just showed us with the column density, that has implications in terms of your size of clouds as well, does it not? If you're going column densities are there, once you go the lower column densities, they could be larger, right? It's just you're not detecting them at the lowest column density.
Yeah, so so basically the one place where I can constrain the sizes is that one sight line. There's only one galaxy.
Yeah, I know, but I was thinking that sight line.
Yeah, so that sight line deserves better, more complete analysis. The B quasar has a significantly lower spectral resolution and signal to noise, so it's a little hard to do the full fitting on it, although I will probably try at some point. But yes, it could be the case that at different column densities or different ionization states, you actually see a significant difference. But I would say qualitatively what it looks like is that in the low ion phase, the absorbers are probably very, very small, but with the likely hotter oxygen 6 phase is much more physically extended.
And you would give a number of clouds along the line of sight.
Oh, so typically there's this is in my paper, so I should know the number off the top of my head, but it's 10 to tens of clouds per line of sight. And that is a larger number than is typically reproduced in simulations. So the only person who's actually looked at this that I'm aware of, so apologies if someone else has, is Molly Peebles, ran one of these enhanced halo resolution kind of simulations. And she finds a factor of 2 or 3 fewer components than we find, although doing the comparison in a way that doesn't make any sense. But my observations weren't out when she published her paper, so. Okay. All right, any other questions? All right, so the physical conditions within the CGM. All All right, so this is fun and exciting and new. This is the first time this has been done in the high redshift CGM or the low redshift CGM, really. So this is a cool thing to talk about. So basically, if we're interested in understanding the physical properties of the gas, what we're going to rely on is the fact that the width of these individual absorption lines actually encodes the temperature and turbulence within the gas in the CGM. And so how does that done? Let me walk you through it. For an isothermal gas cloud, we expect that the velocity dispersion of the gas, essentially the motion of the particles, will be inversely proportional to the square root of the mass of the element, okay? So if we have absorption signals from two different ions that are from different elements that have very different masses, we can actually look for the signature of thermal broadening, which is that lower mass ions have broader widths than higher mass ions, okay? So these are two examples from our data that show very clear signatures of thermal broadening. The carbon signal is significantly like blobbier and wider than the silicon signal. Silicon's much more massive than carbon, okay? So this is an extremely clear for an observer. Apologies if it doesn't seem clear. But for an observer, this is like, oh my God, it's thermal broadening, this is amazing. On the right, I'm now showing the opposite case, which is sort of a bulk motion in the gas. Turbulence is what I'll call it, but roughly speaking, it's really just a constant velocity. So if you have a constant velocity in the gas, you expect the velocity to be constant. And so you don't expect any large difference in the widths of lines for different mass species. And so on the right, I'm showing cases where turbulent broadening is the dominant source. The silicon and carbon lines have very similar widths. Okay, so in practice, every single gas cloud can have contributions from thermal and turbulent broadening. And what we can do is use the fact that we have different mass elements in order to make the measurement of the gas temperature and turbulence. So this is what they look like.
Sorry, Gwen.
Yes.
So you're distinguishing the turbulent broadening from bulk flow, from inflow and outflow, and how do you do that?
Yeah, so bulk flow, I would argue that we can't really measure directly. That has something to do with the offset velocity from the systemic redshift of the galaxy. This is like literally, there's, whatever, 10 to the 12 carbon particles, and it's the relative motion of that within a single cloud structure. So, if there's actually turbulence within the gas cloud, it would look like this, but there could be other, it's not the 200 kilometer per second, say, flow velocity. It's the micro scale turbulence or whatever. Those are probably the wrong words, but does that make some sense? And it's certainly not the turbulence within the whole halo. So that would be better described by the velocity dispersion of the very complex structure that I showed you before. Okay. But that's also hard to quantify because there's a lot of projection effects, which is why I'm not going to talk about it today. All right. Okay, so the gas temperature and the turbulence. Okay, so this is now a histogram of the gas temperature within the CGM with some significant observational biases, so I want to walk you through those. I can't measure gas temperatures below roughly 10 to the 4 Kelvin because it's below the spectral resolution of my data. Okay, so I can't see the difference between those profiles, and so temperatures below roughly 10 to the 4 are not well constrained. I can't measure gas that has temperatures around 10 to the 6 and higher just because I wouldn't see it in the ionization phases that I'm looking at. Okay, so this is not a complete temperature distribution, but for gas that produces UV absorption lines, this is the best we can do. Okay, so why is this interesting? Is this interesting at all? Okay, so we see gas over a very wide range in temperatures, 10 to the 4 to 10 to the 6 Kelvin. So that's kind of cool in and of itself. But I think the thing that's more interesting and made me more excited when I first made this plot was the fact that the gas is mostly not at what I'm going to call boring temperatures, okay? So it's not the virial temperature of the halo, that's 10 to the 6 Kelvin. There could be a ton of gas there that I can't see, but all of this gas is not at that temperature, okay? It's also not at sort of the typical temperature of the IGM, which is 2 by 10 to the 4 Kelvin, right around here, okay? It's also at a temperature scale that's hard to get to just from photoheating, okay? So it's not just that these galaxies produce UV photons, they ionize the gas, and it gets heated. There's actual physical heating processes that are occurring that's not just light. And I think that's really exciting because this gas is basically all at the peak of the cooling curve. It cools down very, very rapidly depending on its density, but even if it's at really low density, it still cools extremely quickly. And so this gas basically has to be continually produced or continually heated. And so I think that means that there's a lot of diagnostic power in these observations. And so I'm really excited about that aspect. Okay, so that's temperature. What about turbulence? I think the main thing that's notable about the turbulence is that it's pretty low. It's not like, we're not talking about huge turbulent velocity values. And in fact, if you quantify it against temperature, what we see is actually the internal energy in the detected gas is almost completely dominated by thermal energy for almost all the absorbers. So you can see over in this right-hand column, 90% of the energy coming from the thermal component is the case for over half of the absorbers in our sample. So the vast majority of the gas is really dominated by its thermal energy. Okay, what else? Okay, so I sort of already said some of this, but basically the really exciting thing about these results is that most of the gas is sort of at these intermediate temperatures. It's not at sort of this IgM temperature. It's not at the virial temperature of the halo, and I think this has significant diagnostic powers. So Drummond, for instance, has published a paper showing that this sort of intermediate temperature gas may in fact be highly influenced by galactic winds. So he's run a set of simulations showing the difference between having a high mass loading, high wind mass loading, and a low mass loading here. And what we see is very different amounts of gas in this sort of intermediate temperature range between the two different simulations. Now, notably, this is for a halo mass a factor of 10 lower than what is likely for these galaxies. And Drummond and I have discussed this a little bit. It may have something to do with sort of the difference between these idealized simulations and what actually the real universe looks like at redshift 2. But I think this points to the idea that this could be an interesting diagnostic of feedback.
Did you mention what the cooling time is for this gas?
So it depends pretty strongly on the density, but it can be as short as like 10 megayear, but it's significantly less than the age of the universe for these galaxies.
I mean, it's a really cool and surprising result.
Yeah. The fact that there's so much gas at this temperature where the gas cools quite quickly is pretty remarkable. Okay, so I think this is one way we can see this might be interesting for winds. There's other interesting work that's come out of Greg's group that has shown that potentially this, I think, also has diagnostic power for other methods for driving winds, such as cosmic rays. So I'm going to have you focus on this top right panel. This is for gas less than 10 to the 5 Kelvin. And these are just different models. Black is without cosmic rays. The different colored curves are different models of cosmic ray diffusion. So I'm not going to talk at length about the difference of these models. I don't really understand them, but I'm sure Greg can talk about them more. But the main point I want to take away is just that they look very, very different. The different colored curves look very different in terms of the total amount of mass at a given temperature. And I think that's really interesting because that suggests that these temperatures can actually be really important for understanding whether cosmic ray driving matters at all at high redshift and to what degree this might be affecting the circumgalactic medium. So I think this is another cool place where we could potentially make a lot of progress. Okay. So just to sum up that little subsection, gas exists at a very wide range of temperatures. I think this is broadly consistent with some of the theoretical paradigm that we have of cold flows plus hot gas from outflows or virial shocks, and that this intermediate temperature gas can be a really interesting diagnostic of those physics. But I think, at least from an observational perspective, in order to make more progress, in terms of understanding whether this intermediate temperature and hot gas comes from outflows or virial shocks, what we would do well would be to understand both the kinematics and chemical enrichment of that gas. So I can't tell you in detail about the chemical enrichment today. That requires more modeling than I'm prepared to tell you about. But I will tell you a little bit about the kinematics. All right. Okay, so can we detect inflows and outflows in the circumgalactic medium, and what can the kinematics tell us about feedback? All right, so to talk about this, first I'm going to tell you a little bit about redshift space distortions in case you guys aren't familiar with the concept. So this is starting instead of gas around galaxies, this is starting from galaxies around galaxies. This is the galaxy correlation function from the 2-degree field galaxy redshift survey. And this displays both of the redshift space distortions that I want to tell you about. So basically there's two principal ones that we're going to focus on. One is the finger of God effect that you see on small transverse scales. This is an elongation along the line of sight that's due to peculiar velocities of the gas, due to the fact that these galaxies are interacting with each other. Instead, on large scales, what we see is the overall compression. This is not a sphere, this is a sort of compressed oval. And that's due, again, to, in this case, the coherent infall of galaxies collapsing onto larger structures. Okay, so we see both of these signatures in the CGM. To show it to you, I'm going to actually collapse it in absolute value so we get higher signal to noise. And this is what it looks like. Okay, so this is looking at it in neutral hydrogen from my 2012 paper and in metal lines from Monica Turner's 2014 paper, both from KBSS data. So we see this elongation on small scales and we see compression on megaparsec scales. So we are seeing cosmological accretion onto these galaxies or the structures around these galaxies. And we do see outflows on small scales, but this is all via sort of a statistical mean, okay? Is there any way to tell that these things actually impact galaxies? All right, so I published a paper now 2 years ago, I guess, where we studied this really unique system, which I'll tell you about very briefly, where we detected a 1,000 kilometer per second solar metallicity wind that contained molecular gas. That turns out to be about 40 kpc away from this tiny little galaxy. These are the kinds of galaxies I study. They don't ever look very impressive on a screen. Turns out that you can learn a lot more from spectra, so you should always look at spectra. So this is what the spectrum of this galaxy looks like. It turns out to be an extremely broad line AGN, very, very AGN-y ionization spectrum. But the more interesting part is that it actually lies below the main sequence of star formation at these redshifts. So this is a case where there's a galaxy, it seems to have driven out some very enriched molecule-bearing gas, and now perhaps has a low star formation rate because of it. So this is kind of like, you know, this is a case where we can point to where we say maybe winds really do affect galaxies, but it's only one galaxy, so how common is this? So what we can do is look at the kinematics of gas within the halo of all the KVSS galaxies, and that's what I'm showing here. So each dot here represents the line of sight radial velocity of the absorbers with respect to the systemic redshift of the galaxy. And it's plotted as a function of the projected 2D distance between the galaxy and the absorber, okay? So I'm comparing these like lower limits on velocity and distance to a 3-dimensional escape velocity profile for an NFW halo with 10 to the 11.9 solar masses, the dark matter halos that these galaxies sit in. That's what this black dotted line is. And what's really notable is that for 70% of the galaxies that have detected metal lines, we see some absorbers that are unbound from the system, okay? So this is in contrast to what is typically seen in the low redshift CGM, where typically absorbers are significantly below, sort of even subvirial from these galaxies. We see a significant population of absorption systems that are unbound from these halos. Okay, so we can ask the question, do these absorbers look any different than the absorbers that are putatively, at least possibly bound? We don't actually know if these absorbers are bound because we only have a lower limit on their velocity. So, but do they look any different? So what we can do is plot up their velocity distribution as a function of now the ionization state of the gas. So the dark blue histograms are showing those absorbers which are formally unbound from the system. So we can see that we have gas in every ionization phase that is unbound. So it appears that the gas that's unbound from these galaxies is multi-ionization and potentially multi-phase, just as the rest of the CGM is. But notably, we more commonly detect this gas in high ions. And very interestingly, it's not typically associated with particularly high column densities of neutral hydrogen. And that's really interesting because what that says is that this gas is typically very highly ionized and may in fact also be high metallicity. And future work considering the ionization conditions of this gas will really bear on that question. But if we take now the 5 galaxies that have unbound gas, what we see is that for those individual galaxies, 20% of the carbon-4 column density is formally unbound. So we could potentially be talking about a lot of these metals that are actually flowing out of these galaxies and may never come back. All right, so in my last 5 minutes, is that about right? I'm going to run real quick through a different idea, which is asking the question what the evolution of the circumgalactic medium can tell us about the evolution in feeding and feedback in galaxies. Okay, so I would argue that we wouldn't expect very much similarity in the circumgalactic medium of redshift 0 galaxies compared to the circumgalactic medium of redshift 2 galaxies. Almost everything about the universe is different between redshift 2 and redshift 0. Galaxies are pumping out stars at high redshift. They're throwing out these amazing galactic winds. The gas accretion rate is probably significantly higher. The IgM looks different. Everything looks different. So we would expect, I think, naively, or maybe even not naively, for the CGM to look pretty different between low and high redshift. So what does it actually look like? How does the CGM change between redshift 2 and redshift 0.2? Okay, so Xiaowen Chen and Cameron Liang looked at this a few years ago. And I'm not going to explain all the details of these plots, but basically they're considering the strength of absorption as a function of distance from galaxies. And what they showed is that high redshift observations from Seidel et al. 2010, that result that I showed you at the very beginning of the talk, suggested that maybe actually there's not much difference in neutral hydrogen between low and high redshift. And at the time this came out, I was just like, this can't be right. Like the observation, like what she's plotting is correct. There's not an issue with this work. It's just I didn't believe that the CGM actually could be that similar. And Cameron went on to show that in fact one could also explain the carbon-4 absorbers as not evolving as a function of redshift. And again, I was just like, that doesn't make sense to me. This doesn't make sense. And so I wanted to look at this now that we have better measurements in the high redshift universe to see whether there was evolution or not. So the question is, with better data, can we see the same trends? And there's a significant complication in this work, which Cameron rightly pointed out, which is that you have to compare very disparate populations at low and high redshift, and that just the fact that you're comparing them across redshift is challenging. Okay, so one of the complications is that, this is in red showing the mass distribution of galaxies in the KBSS sample at high redshift. One can pick out in neutral hydrogen a comparison sample that maybe is similar overall in stellar mass. So that's maybe not so terrible, but in carbon-4 and metal ions, it's basically impossible. The carbon-4 measurements at low redshift are just a really weird hodgepodge. And that's just because of the spectral coverage that exists for UV absorption lines. And so most of the galaxies are actually dwarf galaxies at low redshift that we can do this comparison with. There are a handful of L-star galaxies, but it's like a really small number. Okay, so we have to then be able to normalize across stellar mass and redshift at the same time. So that's kind of complicated. So one of the issues is what is often done in our field is normalizing by the virial radius. But one complication with the virial radius is that even if you have a galaxy at fixed density, the virial radius evolves as a function of redshift because of the change in the mean density of the universe. It's just the definition. So that introduces something that people typically refer to as pseudoevolution, and that's a complicating factor in this comparison as well. So not knowing quite what to do, I will show you all of them, and then I will attempt to say some things that are robust against this normalization. Okay, so if we look in neutral hydrogen, where the galaxy samples aren't so weird, so we can actually just measure as a function of fixed physical distance. Everything I'll show you now is red circles are high redshift galaxies, low blue squares are low redshift circumgalactic medium measurements. This is always going to be column density against physical distance, okay? So what we see if we fit this is a factor of 1.5 DAC evolution in neutral hydrogen as a function of fixed physical distance. If instead we normalize by this virial radius, we actually see stronger evolution, some of which may be due to this sort of pseudoevolution that I was discussing. So we see fully 2.5 DAC of evolution. If instead we normalize by the scale radius of the dark matter halo, which is not actually expected to evolve much of a redshift, we still see a factor of 10 evolution. So this is the smallest amount of evolution that we can get for neutral hydrogen. While the scale radius probably doesn't evolve with redshift, and so that sounds like a really good idea, it does seem a little wild because we're talking about measurements that are at 10 scale radii. And you do actually expect that to evolve with redshift. So it's a little hard to say what the right thing to do is here. But regardless, we see at least a factor of 10 evolution in neutral hydrogen. This made me feel better because there is evolution in the CGM, at least in neutral hydrogen, and that's what I knew the best when these studies came out. So I was like, okay, I'm not going completely nuts, that's great. But what about carbon-4? Okay, so carbon-4, I'm not even going to show you the one at fixed distance. It's not fair because most of the galaxies are dwarfs. So if we normalize by the virial radius, we see a factor of 10 evolution roughly in the carbon-4 column and stays a function of distance. But if we normalize by scale radius, we actually see probably no evolution. And this I find strange and kind of stunning. And I don't have a good explanation for it. My actual explanation is I think we need better data still, which is that I told you that the comparison sample is not great. We're comparing low redshift dwarfs to high redshift L-star galaxies. And what we want to do is compare something like a mass match sample at low and high redshift. And so I am advocating very strongly that we measure carbon-4 at low redshift for a sample that is comparable to the high redshift sample so that we can actually look at evolution in the chemical structure of the CGM as a function of redshift. So that's my case. There are some plausible explanations to this. So you could have actually the CGM be very different, but a change in ionization kind of tricks you into thinking that carbon-4 doesn't evolve. Or you could have something physical that's happening, like a decrease in low metallicity infall. That's a potential way you get more H1 at high redshift and don't see a change in carbon-4. Ultimately, I think it would be really interesting if you have a mass match sample and you see no difference in carbon-4, because that would tell you that the only thing the CGM cared about was the amount of mass that was assembled, not how it was assembled or anything else. I don't think that's going to be the case, but that would be, I think, very, very stunning and very interesting. Okay, so just a few last thoughts. One of the things I'm excited about in terms of looking at redshift evolution is the fact that we're going to soon have a really positive intermediate redshift point to put on all of these plots. And that's coming out of the CUBS survey, which is a large cycle 24 GEO project on HST, where we're getting UV spectra of quasars and going after galaxies between redshift of 0.4 and 0.8. Mary is your local expert on this, so if you have questions later when we start publishing papers, you should talk to her about it. So here's our team. We're really excited. So Xiaowen Chen, Sean, and I are the sort of co-PIs of the study. We've hired 2 really excellent postdocs that are headquartered at Carnegie and at the University of Chicago. So you should keep your eye out for results from this group. And in particular, we're excited because we're going to get quite complete galaxy spectroscopy down to something like a 10th L star across a relatively wide redshift range in order to really understand sort of the CGM of these intermediate redshift galaxies. Okay, so I'm done with my advertising. Aside from this, which is that I am advertising to you all, many of whom are theorists and simulators, that I think if we really want to make progress from these kinds of observations, I've done much of what I can do. And I think what we need to do next is confront some simulations with observations, okay? So in order to do that, what I need from you all is I need CGM predictions for 10 to the 12 solar mass halos at a redshift of 2.3. I need to have measurements of the gas temperature weighted by ionization state of the gas, which I think is very doable from your simulations. I'd be interested in understanding the kinematic complexity of single sight lines, which I think is an interesting test of the small scale structure of the CGM. And I'd also like to see the projected line of sight kinematics as a function of ion phase. These are things that can be very robustly observed. And so I think that they are things that are good benchmarks for simulations. They don't require a lot of interpretation. It's not that I'm going to tell you, the answer and you're going to see whether your simulations match. It's that these are the types of things that this is the ground truth. This is what we can observe. Okay, so that's my plug. And here are my conclusions. I think I'm a little over, so I'm not going to read them all to you, but I hope I've convinced you that the high redshift CGM is interesting and could be very useful for understanding galaxy evolution. That we see very interesting parameters in terms of the gas temperature and kinematics, and this might tell us a lot about the baryon cycle. So thank you guys for your attention.